Have you ever found yourself looking at just a pile of technical information, maybe some practice questions for a tough exam, and thinking, isn't there a quicker way, a shortcut to the really important stuff? Well, that's pretty much what this deep dive is all about. We're taking a set of Snowflake exam questions, but we're not really studying for the exam itself. We're using them as a lens, kind of a shortcut, to get straight to the core Snowflake data engineering ideas that can genuinely save you time, save you money, and honestly, a lot of headaches. Our mission today. Cut through the noise, grab those technical nuggets, and make them really actionable. And we'll throw in some surprising facts, too, about how Snowflake actually works.
Yeah, and that's key because these aren't just abstract concepts or, trivia points. Yeah. They're really fundamental ideas. They underpin how you build efficient, cost-effective data solutions in Snowflake. We want to get past just what these features do and really dig into why they matter for your pipelines and managing your cloud costs.
Okay, let's get practical then. Imagine you're a data engineer. Your boss, maybe a bit stressed, messages you about the Snowflake bill. Or, your key reports are just slowing down. Where do you even begin to look for something that's going to make an immediate difference? Let's unpack how to manage costs and boost performance without getting totally lost in the technical weeds.
Right. So when we talk about storage costs, think about high churn tables. The ones where data changes constantly, lots of inserts, updates, deletes. They naturally generate a ton of historical data because of features like time travel.
Ah, time travel, right?
Exactly. And the aha moment here, I think, is realizing that if you don't need that long history for audits or quick recovery on that specific table, leaving time travel at its default setting can, well, quietly inflate your storage bill. It's like paying for extra storage you aren't really using. So by simply reducing the time travel retention period for those tables, you directly cut down how long that history is kept. And boom, lower storage use, lower costs.
That sounds like a pretty direct way to save money, for sure. But thinking like an engineer, what's the catch? Is there a trade-off? Could being too aggressive cutting time travel bite you later?
Oh, absolutely. Yes, it's a quick win for cost, definitely, but you've got to balance it. You have to think about your actual data recovery needs. Shorten time travel too much on a really critical table, someone makes a mistake, drops data, bad update, and suddenly you might not have enough history to easily roll it back. Then you're looking at maybe a full restore from a backup, which is, much more involved. It's about finding that balance, that sweet spot for each table.
Okay, that makes sense. Finding the balance. Now, speaking of things that seem a bit counterintuitive, how can Snowflake actually speed things up and save compute costs by basically doing nothing?
Yeah, it does sound weird, doesn't it? But it's one of Snowflake's really powerful built-in features, the result cache. It effectively stores the results of queries that have already run. So let's say the same query runs again, maybe it's a dashboard refreshing or a common report someone runs daily. If the underlying data hasn't changed since the last time it ran, Snowflake doesn't need to recompute anything. It just serves up those cached results instantly.
Instantly.
Pretty much, which, dramatically cuts down your compute costs because you're not using warehouse time, and it gives you super fast response times. Think about those internal dashboards people hit all day. The cache means you get instant results, and you're saving potentially thousands in compute credits without doing any extra work yourself. Snowflake handles it.
Right. So the takeaway is you get direct control over spending, faster insights, and often you don't even have to lift a finger. Just need to understand these features are working for you. Okay, shifting gears a bit. Let's talk about data pipelines, moving data, transforming it. This stuff is always in motion. Imagine you need to track every single change happening in a table, maybe almost in real time. You need it for a dashboard or maybe feeding another system. How do you do that efficiently without just reprocessing the entire table over and over?
That's a classic use case for Snowflake streams. Their primary job, really, is to capture DML changes, data manipulation language. So inserts and deletes mainly on a table. This lets you detect exactly which rows are new or which ones have been removed since the last time you checked the stream.
Okay.
And crucially, this makes them perfect for building incremental ELT pipelines. You process only the change data captured by the stream, not the whole massive data set every time. It's a huge efficiency gain.
Right, only the changes. Makes sense. So, okay, you've got streams tracking the changes, but pipelines often have multiple steps, right?
Right.
How do you chain these things together? Manage dependencies, schedules, make sure step B runs only after step A finishes successfully?
Yeah, that's where task graphs come in. They're essential for that. Task graphs let you define those dependencies between tasks quite clearly and even visualize the whole workflow. It makes managing complex pipelines much, much easier.
Uh,
So if you put streams and tasks together, you get this powerful combination for building sophisticated, incremental data pipelines where the schedule is controlled, the dependencies are managed, and you're only processing the necessary changes.
Got it. And what about getting data into Snowflake in the first place? Sometimes you need speed, like near real-time updates, maybe small, frequent bits of data. Other times you're loading massive files less often.
Yeah.
How do you pick the right tool there? It seems like different needs.
Definitely different needs, and Snowflake has different tools. The main distinction here is between Snowpipe streaming and, let's call it, traditional Snowpipe. Snowpipe streaming is purpose-built for that low-latency ingestion,
Mm-hmm.
getting data in very, very quickly for near real-time availability.
Okay.
It supports continuous micro-batching, which is perfect for those high-frequency, small records, think event data, IoT sensors, that kind of thing.
Right.
Traditional Snowpipe, on the other hand, is generally used for loading larger files, maybe less frequently, from cloud storage like S3 or Azure Blob. Latency isn't the absolute top priority there. It's more about bulk loading.
So you've got specific tools tailored for data freshness needs, managing dependencies, handling different ingestion patterns, making sure your data gets where it needs to be when it needs to be, and ideally cost effectively too. Okay, let's dive into the transformation stage now. Materialized views, MVs, everyone loves them for speeding up queries, right? They pre-compute results, but they're supposed to refresh automatically when the base data changes. I've heard, though, there are some surprise situations where they just don't refresh. What's going on there? Why is that important to know?
Yeah, this is a really crucial point, and sometimes trips people up. It affects predictability and potentially data accuracy. The sources we looked at highlight two specific operations that will not automatically trigger a materialized view refresh. First, if you update data in a column of the base table, but that specific column isn't actually used in the materialized view's definition.
Okay, so Snowflake doesn't see it as relevant to the view.
Exactly. And second, if you simply rename the base table itself, both of these actions either change metadata or affect data that's outside the scope of what the MV is tracking. So Snowflake doesn't automatically refresh it.
Right.
And the danger is, if you're not aware of this, you could be querying that materialized view and unknowingly getting stale data, maybe leading to wrong reports or bad analysis just because the underlying table changed in a way the MV didn't automatically react to.
Wow. Okay, so it's not just set it and forget it with MVs. You really have to understand how operations on the base table interact.
Right, and speaking of data formats, JSON, it's everywhere, often nested, right, like arrays within objects within the JSON. Imagine you have customer event data, and one column is just this big nested JSON blob, maybe with an array of products they looked at. How do you actually flatten that out in Snowflake so you can query it easily with SQL? Like, count how many times each product was viewed.
Yeah, that's a super common scenario. For flattening that kind of nested JSON, especially arrays within JSON stored in a variant column, the function you need is lateral flatten. Lateral flatten.
Okay. It's designed specifically to take those nested structures, arrays, or objects and effectively unnest them, creating a flatter tabular representation. Each element of the array basically gets its own row joined with the rest of the data. That makes it super easy to then query with standard SQL, just like any other table.
Perfect. So knowing about these MV refresh nuances and how to use lateral flatten, it means you can build more robust, more reliable data models and avoid those hidden traps that give you stale or unusable data.
Okay, so we've talked a lot about getting data in, transforming it. What about the other side? Getting data out of Snowflake, or maybe connecting Snowflake to external services, things it doesn't do natively.
Right, good point. For exporting data, it's useful to compare copy into with something like select into. Copy into has some distinct advantages for getting data out. Its main benefit is it can write data directly to external cloud storage, think S3, Azure Blob, Google Cloud Storage.
Plus, it gives you options for compression, like using gzip to save space and cost, and you can specify file formats like CSV or Parquet. So it's really flexible for exporting data for other systems or for archiving.
That sounds really handy for interoperability. But what if you need to do something more complex, like run some custom Python code? Or call an external API from within a Snowflake query, but, securely.
Yeah, that's where external functions become incredibly powerful. They essentially create a secure bridge. They let your Snowflake query securely call out to an external API endpoint, often something like an AWS Lambda function or an Azure function.
Yeah, I see.
This means you can incorporate custom logic, Maybe it's a sophisticated machine learning model for predictions, a custom data validation routine, or calling a third-party service for data enrichment directly into your Snowflake workflow without compromising security.
So it really extends Snowflake's capabilities, letting you seamlessly integrate whether you're pushing data out or pulling external processing power in. That's quite powerful. Okay, finally, let's bring it home with some practical troubleshooting. We all want our queries to run fast, right? But sometimes, maybe they used to be fast, and now they're just dragging. Based on what we've seen, what are the usual suspects? The most common reasons for queries slowing down in Snowflake?
Well, there are definitely a few common culprits that pop up again and again. Yeah. One of the biggest, honestly, is the overuse of select.
Still, even now.
Oh, yeah. It's just so easy to type, right? But it forces Snowflake to scan and return potentially way more data than the query actually needs, especially from wide tables. I remember helping someone whose dashboard query took minutes. We literally just changed select to select only the 5 columns the dashboard used, and it dropped to seconds. It's often that simple.
Wow. Okay, select, what else?
Another big one is a lack of clustering, especially on very large tables. Without a good clustering key defined, Snowflake can't efficiently prune partitions. It ends up scanning much more data than it needs to when you filter in your where clause.
Right, inefficient scanning.
Exactly. And lastly, just using virtual warehouse sizes that are too small for the job. A small warehouse might be fine for simple queries, but if you throw complex joins or operations on large data sets at it, it's just going to struggle and take a long time. Sometimes sizing up the warehouse, even temporarily, is the right fix.
So select tape, lack of clustering, and warehouse sizing. Those are definitely key things to check. So maybe the final thought to leave you with is this. Think about the interplay between these features. How does understanding time travel affect your storage costs and your recovery strategy? How does the result cache work with your frequently run queries? How do materialized views interact with your base table updates? Connecting these dots, seeing how these features work together. That's how you move from just using Snowflake to really mastering your data environment. What hidden costs or maybe performance bottlenecks could you uncover in your own work just by looking a little deeper at these connections? Thank you so much for joining us on this deep dive. We hope you found it useful, and we definitely encourage you to keep exploring these concepts.